Today what we're going to talk about is something called a radiation view factor. So again, remembering back to last time, we had this idea of net energy transfer from radiation. So you have a surface, think, like you sitting there, you're a surface, you're emitting to the surroundings. The net radiation idea is that you emit some power, but some power is coming back to you as well. The power coming back to you, normally we call that like sigma times T infinity to the fourth. Well, there's really no such thing as T infinity, right? There's no uniform temperature of your surroundings. There's your person sitting next to you, there's me, there's the wall, there's the lights, right? They all have their own temperature. So when we're talking about radiation exchange, really what we're talking about is the thing we're modeling, that one surface, exchanging with the surroundings, which is a composite, right? It's an amalgam of all these other surfaces that are emitting back to you. So let's say now, all of a sudden, instead of calling it T infinity and lumping everything together, we want to start focusing on individual relationships between one emitter and another emitter. And so to do that, we now have to break out like the chunk of radiation that's going from one to the other surface. And that's called the view factor. So if I kind of sketch out this idea, it might look like this. Let's say we have, let's do it like this. So let's say we have a surface like this, and we have another surface over here like this. And we're emitting radiation from surface, let's call this over here surface I, and then let's call this surface surface J. So the emitted radiation might be kind of in any direction, right? It's leaving this surface from any position in any direction. By the time it sort of goes out to this position, it's basically far away enough where the light's sort of, at that point, it's all coming from one direction. You have it hitting this maybe surface J. So the idea is that only some of the radiation that's leaving I hits J, right? That makes sense. That is the definition of the view factor. So we could just write it like this. A view factor is, we'll call it notation-wise Fij or Fi comma J. So that is referring to the radiation leaving I that hits surface J. So just conceptually, you would say radiation leaving surface I. That goes directly to surface J. And that's going to be divided by the total radiation leaving I. So the one thing to point out here, this is a fraction. It's going to be between 0 and 1. Either 0 is none of the radiation hits surface J, 1 is all radiation hits surface J. And the other thing I want to say is that it goes directly. So it is possible that, let's say we have some other surface down here, right? There's some other surface. It's possible that you might have radiation that hits that surface, is reflected off, and then hits surface J. That's not, we don't count that in the view factor, all right? The view factor is, so just make a red X through this, right? This is not counted. The view factor is what's directly going from one to the other. We will eventually account for that, that extra possible reflection. We get into this idea of something called radiosity and radiation exchange. We account for that, but for the view factor definition, it doesn't include it. Okay, so we have a view factor. How do we use this? Well, the view factor can modify our rate equation. So now if we want to just express like Q dot from I to J, this is now the heat transfer from surface I to surface J by way of radiation. This would be equal to Fij sigma times AI times Ti to the fourth minus Tj to the fourth. Okay, so this is our new radiation exchange model. This is saying from surface I to surface J, the view factor has to be from surface I to surface J, right? And incidentally, if you stop and think, Fi to j, is that equal to Fj to I? Not necessarily, right? Probably not. Like, is your view of the surroundings the same as the surroundings view to you? Probably not, right? There's different fractions there. So once those indices flip around, it's a different number. Yeah?
Is Fij replacing epsilon, or is that you're assuming black body?
Good question. So yeah, the question was, is Fij replacing epsilon? No, it's not. So this assumption is black body, right? This is our black body. We could introduce into this also times epsilon sub I, right? That would make it, we're sort of getting ahead of ourselves, but that would make it a gray surface. And we can include that later on, but let's hold off for now. We're just going to do black body for now. Yeah.
So when you say it goes directly to J, that's just like normal to the surface?
Not necessarily just normal to the surface. It's any radiation that's leaving, like, again, you know, think of me emitting and this wall here is absorbing. So none of the radiation that's coming from me is hitting this surface at a normal, right? It's coming from this angle, pretty steep. But we're integrating the total that's hitting it and that is absorbed. So it's not necessarily normal, it's just like how much is being absorbed total. Any other questions on that? Okay, so the view factor is our way of measuring the fraction of light that it leaves a body and is absorbed by another body. Now we've expressed this in terms of like the source temperature Ti, the receiving temperature Tj, and keep in mind that this is exchange, right? This is an exchange that's happening. Tj is also emitting and being back absorbed by Q dot I, and that's accounted for in this equation, okay? One other thing I want to develop from this is we have this rate equation, Q dot. We always go back and like express things in terms of resistances. So how might I change this equation to make it look more like a resistance? Or what would a resistance be in this case? Well, we can define this new resistance, which is, we'll call it geometric resistance. I'm going to call it R superscript G. This is the resistance due to the view factor between I and J. And this would be equal to 1 over Fij times AI. So this is coming out of the fact that on the left-hand side of this equation, or sorry, the left end of the heat transfer equation there, we have Fij sigma Aij. Remember, sigma t to the fourth is sort of a special thing, or it's like its own thing. So let's just pull out the Fij Ai and make that the resistance, or 1 over the resistance, and then we'll define it this way. The reason I'm calling this Rg and not just plain old R is because it's actually a different dimensional quantity. So the units on this are 1 over meters squared. Right? This is not the same as a thermal resistance. It's a geometric resistance. Why I call it a geometric resistance is it's basically, you know, the smaller that view factor is, that is the less light or the less energy that's absorbed by the target, the bigger R becomes. So the bigger this sort of geometric spatial resistance becomes. So we'll call this R sub G. It's different. It can be combined with other resistances, but not like by adding them up, right? You have to do an energy balance. Okay, so this is, this is our geometric resistance. Okay, so these are really the only kind of foundational ideas that you need for view factors. And then the really interesting part of this, or the only thing that's like challenging, is evaluating them. So how do you compute the view factor Fij? And this is all just like a bunch of geometry now and some other methods. So what we're going to do at the rest of the time is basically go through all the ways, all the tools in the toolbox that you have to evaluate Fij. All right? Okay, evaluating view factors. So first of all, there is a sort of formal definition for the view factor. I won't make you write the equation, but that's what it is up there. let's just walk through what's going on here. So this is saying, if I want to compute the view factor, actually the area of a surface times the view factor, I can do that by taking this double integral. So let's imagine that I have two surfaces. Let me just zoom in over here. Let's imagine that I have two surfaces, surface I here and surface J up here, and I want to compute the view factor between them. What this integral is saying is if I sort of sample over the entire area, AI, and then take the product of the cosine of theta I, right? Theta I is the angle between the normal to the surface and the vector connecting my sampling points. Right? If I take the product of those two cosines and then divide by like the total area available to me, which is pi r squared, it's sort of this like disk that's available to do this, that ratio gives me the view factor. Right? So this is, you can maybe stare at this and convince yourself that it makes sense, but it's basically you're kind of going piece by piece over the surface, looking at all the possible combinations of angles, multiplying them together, the cosines, and then you get back this view factor. So this is like the formal definitions. Why I'm not writing it out is because you don't actually ever use this. So we just want to know that it exists, and it sort of comes from somewhere, but it's not something that we actually will use, at least in this class. So what do we use? Well, I've taken the liberty of breaking it out into three categories. This is my own categorization of things. I would say there's kind of three general ways to evaluate view factors. One is inspection. So you sort of look at the situation, and it is obvious to you what the view factor is. And we'll give examples of that. The second category is something we'll call rules. So this is like a set of heuristics or procedures that you can follow, these general truths about view factors that you can apply that let you, like, if you computed one, you can compute another, vice versa. So we'll go through enclosure, reciprocity, consolidation, symmetry, and then this thing called Hoddle's crossed strings method. And then the last thing is analysis. So sometimes the rules will fail you or are not enough information, inspection's not good enough. You actually need some equations that you can pull out and use. So analysis would be either equations coming from a library of equations or Monte Carlo ray tracing. So we'll talk briefly about all of these today, hopefully.